Hello again. This is Dr. Dan Guerra, and this is a VerEvMed special video lecture. This is Christmas, and I'm recording this right before the actual holiday so that I can be with my family on the holiday. Now, I've been planning this for a really long time. I would say about 4 days, and that's a long time for me because I don't tend to plan things too far ahead. But it's something I've been thinking about for a much longer period of time, years for sure. And it's something I've written about here and there in blogs and in various other communications. And in general, what I'm doing here, and what I will do hopefully this afternoon with you, is try to see how we can combine what is known about Western philosophical tradition relative to some very basics about the association of the cosmos and the self with chemical principles. That's right, chemical principles. Remember, I have a PhD in biochemistry, and so what I tend to do with my philosophical training, and I do a fair amount of reading in the primary philosophical literature, I've been doing it now for quite a long period of time, is I try to understand how these deep metaphysical and epistemological understandings and frameworks and arguments from some great minds and scholars over the centuries and over the millennia may impact with what I understand as a modern scientist. So this isn't without exception, because there have been other great thinkers over the millennia that have also been scientifically trained and are philosophical. And this includes people like Plato, who was a mathematician, and Aristotle, who was probably one of our first natural scientists. Of course, more recent times, we can think of someone like Immanuel Kant, and the list is quite extensive, and I'm not going to get into it right here. What I'm trying to say is that I'm going to try to today do sort of a light but heavily spirited in the Christmas tradition examination of some very important aspects of pre-Socratic and much later philosophical Western tradition as it relates to cosmology and concepts of the self and concepts of interactions with one another in the season where that's so important and where it should be important all the time, the care for other people, and what we know about chemistry. Now, I know that sounds unusual, but hopefully when I get through this and I start talking about it, you'll see where I'm coming from. It's, again, what I do when I have spare time. And it seems like even when I don't have spare time, I do it. So here we go. So the topic of this little talk is the eternal and the infinite. Now, how are those things? Those two terms are pretty complicated, and the Greeks actually didn't like those terms too much, tried to avoid them whenever they could because of their mathematical training. They didn't like things that didn't come to a conclusion. Now, not all Greeks were that way, but some of them were. But the eternal has to do with a time signature, and the infinite more with a spatial signature. And I'll just leave it at that. Now, the subtitle, or a couple of subtitles, is How the World Defies Reciprocity While the Individual Awakens to Freedom of Will. Okay, so that will take some unpacking, but I want to put that out there. And the more colloquial subtitle is All is Not Lost When Nothing is Missing. I know that that's a rewording of some other famous statements like that, but that's mine, and I kind of like it. Again, that's me, Dr. Dan Guerra, and this is a VerEvMed presentation, but it is the kind that doesn't relate specifically to primary research literature. So let's get started. So, question we can ask. What can chemistry tell us about pure reason and empiricism? Those are two major branches of metaphysics. Pure reason is the way of understanding the world without experience. And empiricism is pure empiricism is understanding the world only through experience. So obviously a fusion of the two is somewhere where we might be able to find compatibility in the way that we live our lives. And certainly that's how philosophy has played out, Western philosophy in particular. So pure reasoning requires an indifference to the empirical, but it doesn't occur without it. That's a very important thing. Pure reasoning doesn't mean that people that follow this this line of philosophy feel that there's no reason to consider experimentation or experience. Indeed, that's not the case at all. A very famous member of that camp was Rene Descartes, and certainly Rene Descartes was also a scientist, right? So what people like Descartes were getting into, though, was that if you really want to evaluate the world and the universe around you, you have to know something about yourself. And that the argument he laid out was that the only thing you can really know is that you are now thinking. Because if you weren't thinking, how would you have that thought? And from that, he built an entire metaphysics that became sort of the modern Western metaphysics and philosophy that has run right up to today's ramparts. Pure empiricism is like something like John Locke, or maybe Berkeley, or maybe Hume. And the empiricists, mostly British, as you can tell, were more about, well, nothing in the world can be known just by thinking or reason alone. You need to have experience. Experience teaches you everything, including all the concepts you use, and therefore how you explore and understand your world. Okay. So the empirical strives to corner the ontological, that is what is there, into prediction and determination. Now that throws a lot of other complexities into it, right? So the empirical wants to say, like as a scientist, I'm all about this, right? When we design experiments, we want to say, well, we have this hypothesis, we've deduced this hypothesis, we're going to do some experiments, we're going to tease out something about nature, in my case, something biochemical, molecular, cell biological, something like that. And then we're going to try to get results, and that result hopefully will allow us to determine when we encounter the same, let's say, pathophysiological cancer again, that we're going to get similar results, right? So again, that's kind of like how empiricism works. We come up with deductions, and those deductions allow us to experiment via hypothesis-driven research, and then we make predictions of what that research might say via null hypothesis, enclosure and disclosure, and then ultimately we study the data, we vet it, we look at the evidence, and then we try to make an induction, and that induction is what we think will happen out there in the same similar circumstances in the future. So that's a determination and a prediction. So the rational necessitates, the rational, just pure reason, no quantity, while the empirical is largely qualitative, as it starts in deduction and it ends with induction. So think about empiricism as mostly qualitative, although it uses quantification via the vetting of evidence. Okay, that's where it starts, as a qualitative question. So I would argue that the romance between abstract reason and specific experience actually generates what I call the existential. The existential what? The existential individual, or the existing individual. That is, I believe that we are a fusion of how we think and how we reason inside ourselves and how we experience the world. And there is a relationship there that is mutually inclusive. So existential thinking is what I call being in the world. That is not just existing, but thinking with existence, like knowing that you are a thinking thing, knowing that you are something that reasons, and knowing that you are something that experiences through your senses. That is being in the world, being the verb, not the noun like human being, being the verb. So I also say that while reason requires experience, while reason requires relation, experience is bound to modality. Okay, so reason requires relation, that is, one thing associated with another, whereas experience is bound more to modality, that is it necessary, does it exist, or does not exist? Okay, that sort of modal form, right? What is? So, because that's how your senses work. Is something there or not? Is it real or not real? Those are the typical terms we use. So from that, I say reason is more like enthalpy, and experience is more like entropy, or is entropic. So let me unpack enthalpy and entropy, okay? Because this is where I bring in my chemistry. So enthalpy enters as entropy departs. Entropy gets attention, you probably have heard about it even if you don't have any background in chemistry or physics, because it's used as it's a standard for a cosmological concept. Like all things are leading to disinterestedness and decay. Everything is falling apart. That's how entropy is normally described in common literature. So entropy conjures up often the sublime. I don't know how you get sublime from that. Or something that's out of reach. I guess that's part of it. Or something that's awesome, using 21st century terminology. A word I'm going to quit using, by the way, after the new year. Or maybe something scary or even dreamy. You know, that's what entropy sounds like to people that don't have a clear understanding of how it is qualitative and quantitatively in chemistry and physics, which we're going to show you in a moment here. Now, enthalpy is even less understood. Most people, if you ask a person on the street what's enthalpy, they're going to go, duh. And that's because of bad education. We should teach things, the principles of enthalpy and entropy, in elementary school. And I've done that with when I sometimes guest lecture in, for example, my son's classes ever since first, second grade. My youngest son, that is. Now, what enthalpy describes is quantitative and qualitative in detail. And it basically describes the existing ontological state because it has to do with basic thermodynamics or heat transfer. So enthalpy is the basis of biochemical reactivity, bioenergetics, and indeed, I argue, the temporality of existence. That is, remember a while back, in many of my lectures, I've talked about aging. Aging is the temporality of existence, right? How long do you live? How long are you existing? So I argue that we thrive and die under the direct influence of what is called the delta H, or the change in enthalpy. Now, you need to know this equation. Delta G, and G is Gibbs free energy, is equal to delta H, which is enthalpy, minus the absolute temperature T times delta S, which is the change in entropy. Okay, that's called the free energy equation, Gibbs free energy equation. Now, when that result of solving that equation is negative, when the equals past the equal sign is a negative term, that means that it's going to happen spontaneously. That means it's likely to occur in nature. If it's positive, it means it won't occur in nature, and unless something more negative at the chemical level will counteract or spin those terms into being plus to minus signs. Okay, all right, you'll see. So the change in the internal energy of a system is equal to the heat added to that system minus the work done by that system. So we use the delta Greek letter for change. That's the change in the internal energy. And for that, we use a capital U. And we say that's equal to Q, heat added to the system, minus W, which is work done by the system. Now, this is basically a thermodynamic equation, which helps us understand how energetics works and how objects exist in their surroundings, either open or closed systems. Again, this is like causing recollection for you, a Platonic term, which we'll get to soon, from your physics or chemistry in high school or college. Hopefully, most of you have learned this at some level or another. Then I'm very pleased. But you will see why we're going very abstract, because we have to go abstract for you to really appreciate and understand these chemical terms. Otherwise, there's no sense in trying to embellish an argument that associates chemical thermodynamics, which is what I'm doing today, this Christmas, with a certain reflection on traditional Western philosophy. Okay. And again, that's why I'm doing this, right? So let's tear apart this equation. This is rewriting the equation, basically. But Gibbs free energy G equals the internal energy, which we already talked about, minus the TS, which is the final entropy. Notice there are no deltas here. This is just a straight up equation. Now, that T times S is the energy you can get from the system's environment by heating. Remember, a system is embedded in a larger system called the surroundings. Now, you have to add to that terms that we got from the gas laws. Now, I'm not going to go into all the gas laws and how we got to these kinds of equations by studying the properties of gases in closed containers, but that's really where this comes from. So we have to add pressure times volume, and that's going to be an important component here because, again, this is quantitative. It's something you can measure. And PV then is basically the work to give the system the final volume at a constant pressure. And those two terms are really important in determining what kind of work you can get out of internal energy and whatever energy you get from the surrounding, okay, which is what entropy is in the straight up. So let's go back and let's redefine enthalpy. Enthalpy term is H, capital H, is defined by U plus PV. Remember that U is the internal energy of whatever it is, the system or the molecule or the atom. And P is the pressure, and V, of course, is volume, again from the gas laws. So the enthalpy is a Greek word which means in enthalpos, heat. Okay, so this is why it's called thermodynamics, right? It was formerly called heat content, and the symbol enthalpy is H. Why do we use H? I'm going to go right down and tell you that from as far as I can determine, H is used because it's the first letter in heat. And heat content, so that's why they chose it. The name heat content was dropped somewhere during the 19th century, probably early 20th century, maybe in some textbooks, to avoid confusion with heat capacity, which is quite different. But the symbol capital H is retained to represent enthalpy, and that's good because we don't need to do anything about changing the stand-in, right? We don't need to change the nomenclature. We should probably avoid that when we can, because it just adds confusion. Now, enthalpy is an extensive property. As chemists call that an extensive property. And what that means, basically, the value, the amount of enthalpy you can measure depends on the amount of the substances present in the system. So it has to do with the amount of substance. So the larger the amount, the larger the value of H. Okay, so that's where we get the quantification. Okay, we call that an extrinsic versus an intrinsic property, which is not dependent on the amount of substance. Now, I also want to bring up a very important definition, the importance of state. The heat exchange in a reaction will depend upon the states of the reactants in our products. Take a look at this. Here we're looking at an enthalpic equation, the delta H. We see it's negative for this particular reaction. So C3H8 plus 5 molecular oxygen molecules will go to 3 carbon dioxides and 4 waters. Now notice all 4 of those reactants are gases. Notice that the delta H is minus 2043 kilojoule. That's an energy term. Now take a look at the same reaction, only we're going to turn the water into a liquid. It's going to condense. So the reactants are the same, C3H8, it's a gas, 5 molecules of molecular oxygen will go to 3 carbon dioxides and 4 waters, just like before. There's no change in anything in terms of reaction of products, except that now the water is a liquid, it's condensed from the gas. So notice that that number is what? It's increased, right? So the additional heat, now this is heat release, remember that's what enthalpy basically is, into the surroundings, is higher, okay, because of the condensation of water. When you condense water from a gas, you release exactly 176 kilojoule of heat. Okay, see how that works, right? So the state matters. In other words, liquid, solid, gas. So now we can talk about a thermodynamic standard state. So heat changes will also depend necessarily on pressure and temperature. So the standard state we define as the most stable form of a substance at 1 atmosphere pressure. That's what it is at sea level on Earth. And 25 degrees Celsius, which is the temperature that's considered the normal, basically lab temperature. And then 1 molar concentration for solutions. Okay, so don't worry about molarity. I hope that some of you are familiar with it. I'm sure all you professionals are. And sometime we'll just go about and talk about molarity and Avogadro's number and all that, but not today. Just 1 molar concentration for solutions. So conventionally, enthalpy change under standard conditions is presented by this, delta H naught, not superscript. Notice, okay? That's how it's written. So any thermodynamic function referring to standard conditions is always going to be identified by that, looks like a degree sign, right? Which is going to be in the superscript. All right. So let's calculate the change in internal energy from the change in enthalpy. So the reaction between nitrogen gas and hydrogen gas at a pressure of 40 atmospheres, that's 40 times the pressure that you get, at sea level on Earth, and a change in volume of, let's say, a decrease of 1.12 liter. So there's your equation. Nitrogen gas and hydrogen gas go to 3 ammonias, which also are a gas, and we're going to have an enthalpy of minus 92.2 kilojoule. That means that reaction is going to proceed from left to right. That negative sign always means that. So let's now determine delta U. We plug into that equation all these terms. So delta U equals minus 92.2 kilojoules, minus 40x, minus 1.12 liter atmospheres. Remember, that's going to be your volume change. Multiply that then times what the equivalents are for how many joules per liter atmosphere. And of course, 1 kilojoule is 1,000 joule, right? And you end up with a number that for the internal energy of minus 87.7 kilojoule. Now, in this particular example, the delta U is greater than the delta H. Remember that these are negative signs. So a negative minus 87 is larger than a negative minus 92, right? It's closer to unity, right? Okay, so that number, that overall number is larger. So internal energy change is less negative. It's less negative by amount of work done by the surroundings on the compressing system, okay? So internal energy does not actually equal enthalpy, right? Because some work has been done on the surroundings because of this reaction. All right. So enthalpies of change of state are simple to understand, I think. Let's just do this quickly. So the conversion of a substance from one state to another involves heat input or output, of course. Heat is absorbed when breaking bonds. So that's like when you go from solid to liquid to gas, heat's absorbed. And the heat's released when you go the other way, when a gas condenses to a liquid, as we saw in that first equation, and when the liquid finally solidifies to a solid, like, for example, gaseous water to ice. So the heat of fusion, vaporization, etc., are all formally known as latent heats, and that's where heat is consumed, and of course there's no formal change in the absolute temperature. So you see here that we go from solid to liquid, we call that melting, and liquid to gas, we call that evaporation. Energy is absorbed. When we go the other way, gas to a liquid, we call that condensation. Liquid to a solid, we call that freezing, and energy is released to the surroundings. Okay, so how important state is. So another important thing to remember, there's so many concepts, but bear with me, these are important. State functions ignore the path. So the transition from solid to gas may lie through the liquid phase, as we just saw. Or the transition could be direct. You can sublimate. For example, when the snow on this mountain over here, when the sun comes out tomorrow, the snow may sublimate. It go from the solid snow directly to the gas, right, and make fog over the river. Right? That's a sublimation. But the enthalpy change is the same, okay, because you just add the delta H of fusion and the delta H of vaporization, and that equals the delta H of sublimation, okay? So that says it ignores the path. So even if you go first to liquid and then to vapor to gas, it doesn't matter, the delta H will be equal even if you go directly from a solid to the gas. That's important. So another thing to consider, the heat of the reaction. Enthalpy change for a reaction is commonly known as the heat of the reaction. Exothermic reactions refer to when the reaction where the heat is given out by the system, okay? We warm our hands. Delta H is less than 0, okay? An endothermic reaction refers to when the heat is absorbed by the system and the surrounding gets cool or hands get cold. That's where delta H is going to be greater than 0. Notice those signs of delta H, very important. So there are multiple ways to calculate the delta H naught. Delta H naught could be quoted for a given equation for 1 mole of reactant or product, as we said, standard conditions. Either way, it can be used to calculate the heat change for a given amount of substance. Okay, so that's all I want to say about enthalpy. Much more we could do, many more equations we could do, many more examples, including biochemical examples, but that's all I want to do with this today. Now, let's switch to entropy. Let's go back to basics. Entropy is also Greek for the word trope, and trope simply means change. Isn't that interesting? Okay. So N, of course, signifies as a thermodynamic property involving energy, and S is for a very famous scientist named Sadi Carnot, and so that S is for Sadi, for his first name. You might have heard of the Carnot engine. Energy is defined as the capacity of a system to do work, of course. Entropy quantifies the ultimate dissipation of a system to do work. Thus, entropy becomes that unavailable or pure energy where no enthalpy is involved. Okay? So if you dissipate the system to do work, that energy is not available, and but it still exists. And that's where arguably the cosmos is going. The universe is going to a state of pure entropy where no energy is available. So pure energy is unavailable since there's no matter in the system any longer for energy to work upon. And so entropy implies, this is where some of this dreaminess comes in, randomness, right? Randomness, where everything kind of falls apart or becomes random coils, let's say from a double helix, to use the DNA metaphor. The greater the randomness, the greater the value of the entropy. The larger is the value of entropy. Okay. So for example, the entropy of a substance of a gaseous state is greater than the liquid state, is greater than the solid state. Boom. Okay. I'm getting some of this from this particular link if you want to go and look up a lot of what's discussed about entropy and enthalpy. So remember the second law of thermodynamics. Remember it. Of course, I know you do, just as when in one of the Platonic dialogues, when Socrates proves that the slave boy actually does know something about mathematics, it's argued that he remembers it or he recollects it from where? From when his spirit or soul existed in the forms. Okay. If you know what I'm talking about, fine. If you don't worry about it. I'll bring it up a little bit later. At any rate, remember the second law of thermodynamics, back to chemistry. Any irreversible process results in an increase in total entropy, whereas any reversible process results in no overall change in entropy. In other words, it remains equal, or it's rendered, the final entropic term is rendered without change. Now, the entropy of the universe can increase in any spontaneous process. So, two bodies in thermal equilibrium are at the same absolute temperature. Energy can neither be created or destroyed. I know you've heard this. So the change in E equals Q plus W, right? So we know this already, heat plus work. The total entropy of the universe is the system plus the surrounding system, being whatever chemical system or living system you're talking about. But the universe has to also include all the surroundings because the universe is universal. It's everything. So, therefore, the entropy of the universe must increase in every spontaneous process. So the delta S total equals the delta S of the system plus the delta S of the surroundings, and that's got to equal 0, okay, because of conservation. Now, the entropy of a pure, perfectly crystalline compound at temperature of 0 Kelvin is 0. So there's no disorder in there. But remember, this is a theoretical state, okay? So that never, ever, ever happens, except maybe at the very end of space-time, okay? All right. So entropy, like enthalpy, is an extensive property. The value does depend on the amount of substances present in the system. Entropy is also a system that is a state function. It depends only on the state variables, temperature, pressure, volume, and the number of molecules. Thus, this change of entropy is given by delta S, where delta S means the entropic state final minus the entropic state initial. Okay. Delta S. The delta means change. Remember the Greek letter. Now, entropy, which is funny because tropa itself means change. Entropy change of system, that is the delta S of the system, does not depend on the path followed by the change. But the entropy change of the surroundings does depend upon the path. Okay, so there's a difference in whether or not this acquires the same properties of state functions. If you're talking about the entropic state of the entropy, the entropic state of the surroundings versus the entropic state of the system. So that's because of the total entropy change of an isolated system is equal to the sum of the entropy change of the system and that of the surroundings. Remember this equation. That's why it must be this way. So the total entropy change of an isolated system is also called the entropy change of the universe, or delta S of the universe. This is a type. And remember, the universe can also be treated as an isolated system. We can talk about the universe as a whole thing. Okay. So In a reversible process, the change in entropy of the system equals the negative change of the surroundings. In an irreversible process, the delta S total is always greater than zero. This implies that in a spontaneous change, there's an increase of entropy in the universe. Irreversible processes tend to be spontaneous, and we have plenty of them that we can point to in nature. So entropy is a measure of disorder in the universe, where the natural tendency of the universe is to move from order to disorder. Now we're going to start getting into Platonic philosophy. So if we go to order to disorder, we go from lower to higher entropy. Now, in Platonic understanding, metaphysics of the universe, order is all about the forms, and the forms are those properties of the natural world, which we don't experience, the noumenal world, that are used to form the phenomenal world, or the world that we exist within, the pure forms. Keep that in mind. So this is a fundamental flavor of the second law of thermodynamics, okay? That basically you go from order to disorder, and that's where the universe is headed. Think also about the Big Bang. You had this super small, highly compact form of some matter, maybe pure matter. And that matter spontaneously exploded or disintegrated, and energy was released, and that energy drove all of the production of all the elements that now exist in the universe, as well as all the things that are made up of those elements, like the stars and the planets and the living things on them, like people. Okay? So remember that we're going from, again, a state of order, so that small substance, right, that singularity at the beginning of the Big Bang is like pure order, right, is completely coherently absorbed unto itself. And that then starts to fall apart after the Big Bang. And we're somewhere in some stage of that Big Bang, according to modern cosmology and physics and chemistry. So this is really important for a lot of different disciplines. And a quantification of entropy is necessary to assign an increase or decrease in the system's disorder, because this is what we need to know in chemistry. And this is a practice that's given as S equals Q reversible divided by T, where S is entropy, Q is the quantity of energy transferred as heat measured in joule, and T is the temperature in degrees Kelvin. So that's how we're going to get the term and the properties of entropy, joule temperature. So the quantity of heat transferred is dependent upon the amount of matter in the system, as we said, extrinsic, and is therefore extrinsic, right? Intrinsic properties, by comparison and contrary, describe something about the nature of matter itself that is not dependent upon its quantity or the forces acting upon it. Okay, so keep that in mind. So entropy then, which is universally given as J over T, I told you that's the term we use, right? Those are the units we use, is a state function with extrinsic property. Okay, so it's just like, for the system anyway, just like enthalpy. So I'm going to throw this in before we get into the philosophy. So biochemical free energy is something we teach in biochemistry class, very beginning, maybe the very first lecture. Remember back to delta G, free energy equals delta H minus T delta S. And we're looking at this reaction here with methane and oxygen, both gases, going to CO2 and water. We're going to make it a liquid, so it's going to be some extra heat for condensation. And we're going to say this reaction, the heat content of the reaction, has to surpass an activation temperature, or an activation energy, and that activation energy allows for it to be an exothermic reaction. Heat is lost. And then the delta H, the heat evolved, is somewhere around minus 890 kilojoule. So you end up taking methane and oxygen and turning it into carbon dioxide and water. This is a combustion. And combustions are very common in biology. That's why I chose this particular reaction coefficient dynamic. Now, the change in free energy is the actual energy available to do work in, say, a biological system. It approaches zero as a reaction reaches equilibrium. So when you hear about equilibrium, you always hear this And it's made to sound like it's a great thing. Equilibrium means basically death. Nothing happens at pure equilibrium because there's no change. Without change, there is no existence. That's how it is in chemistry. That's how it is in physics. That's how it is in biology. And that's how it is in philosophy. So the delta G, the change of free energy, predicts whether a reaction is favorable or spontaneous. And it's dependent upon enthalpy and entropy, as we've been saying. The delta H is the change in enthalpy. And it requires the observation and measurement of heat released or absorbed during the reaction. It does not predict, though, whether or not the reaction is favorable. It has nothing to do with it. It only gives you the change in enthalpy. Likewise, the delta S is change in entropy, as we've been saying. And it's a measure, some argue, for randomness, right, or isolation from the component parts, or purity from the complex, the simple from the complex. And it does not predict either whether a reaction is favorable. So neither one of those terms alone can do that. Only a combination. So we can argue that reactions go to completion in a universe of non-reciprocity. What do I mean by that? Well, let's say you have a china teacup and you're holding it in your hand and you're standing in a beautiful stone floor church in central Italy, and you accidentally drop that china teacup. It hits the stone floor. That cup shatters, right? There's no way that cup will ever reform the way it was, right? So non-reciprocity, right? Entropy moving towards entropy. We see it all the time. We experience it. It's part of our empirical world. So let's go now to a biochemical example. Carbon dioxide lost during a decarboxylation reaction. Let's say, pyruvate dehydrogenase, a decarboxylation reaction, which involves the production of acetate, eventually acetyl-CoA from pyruvate, and of course carbon dioxide. CO2 lost during that decarboxylation is not simultaneously reassimilated with acetate, which would be to the same reactant, at the same time. So this is part of the square of opposition, or discussing the excluded middle term. You can't have all S's P and no S's P at the same time in the same place, right? So it's the excluded middle term. So here we're starting to introduce logic into our understanding of chemistry, which of course is where chemistry came from, right? Mathematics is a form of pure logic. So reversible reactions are directionally driven by thermodynamic forces. They're organized around, however, irreversible reactions. So if we look at biochemical pathways, the initial introduction of, let's say, a carbon source into a pathway involves what is essentially thermodynamic irreversible. And then the rest of the reactions that are in that pathway could be freely reversible, but they never are, because the final reaction, the ultimate reaction, is also thermodynamically reversible. And that's how we proceed, sometimes with the input of energy, like with ATP in biochemical bioenergetics, for example. So that's really important to consider. The system remains constant, therefore, while the objects therein transform, until increasing entropy collapses that entire free energy equation. So when entropy keeps on increasing and increasing and increasing because of the surroundings, right? Ultimately, the reaction just goes to completion. There isn't any stop in the reaction sequence. And entropy will eventually override the enthalpic forces. That's because the system gets smaller and smaller, and the surroundings get larger and larger because of this lack of reciprocity, or returning to the beginning. Free energy then drives the reactivity, but enthalpy and entropy alone don't predict whether or not the reaction occurs. So you need to have the association of enthalpy and entropy to be able to predict the free energy. Right? Remember that from our Gibbs free energy equation. It's all very important. So now let's jump right into a metateleological inference from this long discussion. Plato's universe and the prospect of God, his God, was embedded in his metaphysics. And you find that if you read carefully, thoroughly, and study some of his dialogues. It's not just there, but the ones that I would recommend if you want to know where I'm thinking from are the Republic, the Timaeus, the Theaetetus, the Parmenides, and Laws. various stages of his opus, Plato's opus. Plato's views, however, I find actually suggest that he read or understood a pre-Socratic philosopher, a Sicilian named Empedocles. Now, I know this and I'll show you later why, but Plato suggested pure matter, remember we talked about this before, is nothing in particular. He's not necessarily saying it's nothing. He's saying nothing in particular, right? So pure matter isn't an apple or a stone or a glial cell or a liver or a thought, right? Pure matter, thought meaning the neural correlate of thought in the brain, right? The transmission of signal transduction pathways and action potentials, right? That kind of physical chemistry. So nothing in particular is pure matter. So that means to me that since pure matter is nothing in particular, okay, being therefore is a privation of all form. Okay, it's a privation of all form. Existence is the process of becoming, okay, becoming, and then being is the actual participation in the form. So what I'm trying to say is even during the process going from nothing to be, that is non-being, okay, being in privation is non-being, that's what I meant by that complex sentence, to becoming, so you go from non-being to becoming to being. That is part of a very beautiful, complex metaphysics that Plato plays out in his various Socratic dialogues and other places. So that's what he's saying, okay? So in my view, I can read this and I can extrapolate. I'm a scientist, so I like to extrapolate. And I say, in my view, pure enthalpy is where nothing happens because you need to have entropy, okay? So the delta is the becoming, the change is the becoming, and that is existence. And pure entropy is the form or the individuated form, okay? And rather than see this as a cycle, I see this as a vectorial movement towards the beginning to the end, or like the Big Bang to the frozen out, completely differentiated universe at the end of space-time. Okay. So let's do some metaphysical correlations here. It's about time. Free energy can be substituted for freedom of the will, okay? While I would argue enthalpy stands in for shared love, okay? So that is that, remember that the heat that's absorbed, the amount of heat that needs to be absorbed or released during chemical reactivity when bonds are broken or formed. And we can describe that as love, or that kind of interaction which requires participation. And entropy is more like pure individuality, right? Where all of the parts that are associated in molecules, for example, that generate enthalpic properties are now completely separated out. All the bonds are broken. Therefore, pure individual, pure form, right? Or pure being in Platonic terms. So you could argue that the infinite struggle is between individuals, right? Going from this pure undifferentiated matter, right? Where basically there is no true existence, right? Because there's nothing in particular. There are no people involved there. To pure individuation, where likewise there isn't any self any longer, but there's still being. So going maybe from matter to energy, or matter to substance, and substance, a component of substance could be energy. Okay? So in the end, entropy requires the death of the individual. The individual self in this system cannot survive complete de-differentiation, right? Ultimately, everything falls apart. The teacup crashes to this stone floor in Rome. So knowledge of that existence, I argue, knowledge of this information, knowledge of our own existence is what being in the world is. And we are humans, and we're rare in that we have this knowledge of existence. It could be argued that all other objects in the universe that we are aware of don't have this knowledge. At least they're not communicating it to us. So this leads me to even more theory, a theory on rational psychology, which I hesitated to put in here, but I had to because it's Christmas time and I really like trying to put chemistry into philosophy. And part of philosophy is rational psychology, as well as cosmology. Right? So rational psychological perspective. Humans seek each other as a correlate to the reversibility of reactions. That's part of that enthalpy. The donation, for example, of electrons from an electron-dense portion of a molecule to an electron-deficient part of the same or a different one, right? That is what we're talking about, right? So the electron-dense donor in this system in chemistry would be called the nucleophile, and the electron-deficient acceptor is called the electrophile. This is how reactivity occurs, chemistry. So this attack or donation usually results in the formation of a bond, okay, like a bond between two people, for example. And that bond in chemistry is between the nucleophile and the electrophile. And basically it generates neutrality. So once you form the bond, right, you form, let's say, a relationship. And that's what we're talking about here in chemistry. But you can think of the same thing in rational psychology. You form a bond between, say, one individual and another. Then there is some neutrality about that bond where one individual doesn't necessarily supersede the other individual, at least not all the time. There is a feedback. There's a yin and yang. So what I want to say then is this attack or donation usually results in the formation of a bond between the nucleophile and electrophile, and that's a useful chemical metaphor. The bond is broken, however. It can be broken, and it will be broken eventually by either a substitution or elimination reaction, for example. And when that happens, delta S is increased, or in our physical example in the Roman Church, the cup hits the stone floor. The relationship is just no more, destroyed. So in this way, self becomes isolated and once again seeks fulfillment. The extrinsic properties of the participants, right, results in the variable strength of the body. So that the nature of the essence of the individuals who have come that way by being existing individuals, the strength or the weakness of the bonds that form the relationship. And that tells you how long, in rational psychological terms, that relationship might exist. Now, when bonding is too strong, the individual is lost to pure enthalpy. And all of this is a constant heat exchange. This is a place where nothing in particular exists, right? The individual becomes lost in the relationship. Again, this is a rational psychological theoretical launching, right? That's all it is. Now, ultimately, entropy increases, just like it does everywhere in the universe. And again, knowing this process produces maybe the longing and existential anxiety of what it means to be human. Anxiety being the principal, authentic way that people deal with their world. We're always anxious. We always know that things will fall apart. We always know, for example, that we will die. Okay, that's what I mean by anxiety, right? A principal aspect of our affect as dictated through our consciousness and our inward self. So, therefore, I say reason supervenes existence because we know this, and that's what instantiates the human experience, which is being in the world. Being in the world, not just mere existence. So, now, finally, let's get to way back to Empedocles, the Sicilian philosopher, the pre-Socratic. Now, part of this diagram I got from a philosophical site that shows you the cosmogenic cycle of Empedocles, and that's just here. Pure domain of love or harmony, contention between love and strife, pure domain of strife, which they call chaos, completely differentiated, right, completely separated, And then moving back, because Empedocles saw this as a cycle, the contention between strife now being still dominant over love, but then eventually complete harmony. So I've now embedded my chemical formulation for this. I would argue that when we go from pure matter, where delta S is 0, right, and this is an infinity sign, the pure domain of love moves towards the contention between love and strife, and this is increasing in entropy. Right? That buried self, which is nothing in particular, starts to become two individuals. Ultimately, full entropy is reached, and you have only delta H equaling 0 and only delta S. This is also could be considered pure energy. And with pure energy, there is basically nothing, just like there's pure matter, there's nothing in particular. Because there's no matter for interconversion. There's no self. And again, I use the infinity signal. Because who knows the trajectory and the vector of this system? But I argue it's not a cycle, because this whole system is moving towards pure entropy. We know this from chemistry and physics and cosmology. We know this from discussions of the Big Bang. We know this by the Hubble telescope. We know this by chemical reactivity. We know this by the teacup falling on the stone floor in the Roman church. Anyway, if we take things that are purely entropic and we increase enthalpy, we start adding back this strife, this energy system that is involved in heat interactions, thermal interactions, because of the extrinsic properties of material inclusion, right? In-breaking material inclusion, then ultimately we might go all the way back to this domain once again where pure matter is and there's no individuals. Again, this is Empedoclean cosmogenesis. But what I tried to do is explain this in terms of chemistry, in terms of entropy and enthalpy. And that's basically where I wanted to get in today's Christmas lecture. So let me finish by saying this is a picture actually of the Continental Divide in Colorado, where my son and I were a couple of years ago. Here's the email address for VerEvMed, info@verevmed.com. There's our website. Remember that not necessarily shown here in today's lecture, we are scientists verifying published evidence in medical biosciences. This is my Facebook. You can go to that and find all my lectures, most of which, like 99% of them, are not theoretical, philosophical, metaphysical, but are more biochemical, molecular, and biomedical. And go to my Facebook page for that, and also for other interesting things that you may find. That's me, Dr. Dan Guerra, and that is my email if you want to contact me directly about this particular video or any other one that you might want to discuss that you've seen on YouTube. So thanks a lot for your attention from me and from VerEvMed Studios in the beautiful Pacific Northwest, where it's snowing over the Clearwater River. I want to bid you a very Merry Christmas. And I hope that you're with your family and that you're enjoying your loved ones here today. Have a great day. Bye for now.